of corrosion process, it is necessary that long-term structural performance should be treated based on the reliability concept and method. So stochastic treatment of structural design problems takes into account the uncertain nature of structural performance. This figure shows the framework for estimating the life cycle reliability of concrete structures in an aggressive environment. This consists of 3 steps: frame A, B, and C. So including estimation of structural capacity of corroded concrete components, hazard assessment associated with environmental stressors, and time-dependent structural reliability analysis with LCC analysis. So today I will present some studies relating to this framework. So in frame A, structural capacity of corroded RC structures based on inspection result and monitoring is defined. So to make possible the improvement of estimation accuracy of corroded concrete component, it is very important to identify the spatial distribution of cross-sectional area of corroded rebar. So today I will present the X-ray photogram technique to visualize the spatial distribution of rebars. So X-ray photogram is a very suitable tool to visualize the rebars embedded in the concrete. So in frame B, so some methodologies for quantifying environmental effects is discussed. So today I will present the computational procedure to establish the hazard curve associated with airborne chloride. So to establish maintenance plan, maintenance strategies, it is very important to consider the differences in marine environment. So this hazard curve can quantify the effect of marine environment. So in frame C, the time-dependent structural reliability with updating is estimated. Reliability means the likelihood of failure of structures. So the magnitude of reliability depends on the statistics of random variables used in the reliability estimation. So for existing structures, we can use inspection result. So the statistics of random variables can be updated to be consistent with the inspection result. So this is an inverse problem. So today I will present time-dependent reliability analysis with updating. So next I will present estimation of steel weight loss estimate using X-ray photogram. So because structural capacity of RC member, corroded RC member, depends strongly on localized condition of reinforcement. It is very important to model the spatial variability of steel corrosion. However, steel corrosion can be only observed after severely damaging the concrete members. So in order to understand the growth process of steel corrosion and how the spatial variability of steel corrosion increases with the time, continuous monitoring is necessary. But how can we monitor? So in our study, X-ray photography is applied to observation of steel corrosion in RC members. So first, steel weight loss of rebars corroded by electric corrosion is estimated by weight measurement. Then rebar is embedded in the concrete. So concrete with corroded rebar is taken by X-ray. So comparing the steel weight loss estimated by weight measurement with that estimated by the digital image processing, so applicability of X-ray photogram for the quantification of corrosion loss of rebars in RC members is demonstrated. This slide shows the X-ray apparatus used in our study. This includes X-ray generator, X-ray image intensifier, personal computer to visualize the rebars in the concrete using digital information associated with radiography images, and the operator control panel. So specimen can be rotated like this to take X-ray with different viewing angle. So in the experiment, first, concrete specimen is exposure to X-ray. Then X-ray penetrate through the concrete specimen. So by using software to make an X-ray photogram, so the rebars in concrete specimen can be visualized. So intensity of X-ray after penetrating through a material can be quantified by using this equation. So generally, intensity of X-ray after penetrating through the concrete is higher compared to that after penetrating through the rebar. So based on the differences in the intensity of each pixel, the edge between rebar and concrete can be detected by digital image processing. So intensity of X-ray after penetrating depends on the thickness and density. So the effect of water to cement ratio and the effect of the shape of cross-section on the intensity need to be investigated. So experimental parameters include water to cement ratio, shape of the cross-section, and the degree of steel corrosion. The magnitude, the target values of averaged steel weight loss over the entire rebars during the electric corrosion was set to 0%, 1%, 5%, 10%, and 15%. So comparing the steel weight loss estimated by digital image processing for cylinder specimen. With that for prism specimens, the effect of distance between rebar and concrete surface can be examined. So as I mentioned, rotating the specimens, rebar in the concrete specimen can be, rebar in the concrete is taken at the intervals of 30 degrees. So it should be noted that even if X-ray photography is taken at the intervals of 15 degrees, so estimation accuracy of steel weight loss was not improved. So I explained the procedure for estimating the steel weight loss based on the digital image processing. So this consists of 3 steps. So this is the typical deformed rebar used in Japan. So this is the X-ray photogram of rebars embedded in concrete. So when rebars without corrosion is exposure to X-ray, so you can see wobbly surface of deformed rebar can be observed. As steel weight loss increases, the surface of deformed rebar becomes smoother due to the corrosion, like this. So anyway, so using the X-ray photography, we can confirm that rebars embedded in the concrete members can be visualized. So however, the density of corrosion product is less than that of rebar and higher than density of concrete. So the edge between concrete and corrosion product, the edge between corrosion product and rebar are very vague, very unclear on the X-ray photograph. So image processing filter to enhance the edge contrast of an image is used. The filter works by identifying edge boundaries in the image and increasing the image contrast in the area around the edge. So these pictures are examples of X-ray photogram before and after applying edge detection to X-ray photogram. So you can see boundary between rebar and others very clearly. So as I mentioned, X-ray photogram is taken at the intervals of 30 degrees. So from each picture, averaged diameter of corroded rebar is estimated. So using many pictures with different viewing angles, the volume of corroded rebar is calculated. So finally, we can obtain the steel weight loss by using X-ray photogram. So this figure shows the relationship between steel weight loss estimated by weight measurement with that estimated by X-ray photogram. So you can see estimation accuracy is independent of the magnitude of steel weight loss. So without severely damaging the reinforced concrete structures members, so using X-ray photogram make it possible to estimate the steel weight loss. This is a very suitable tool. So, but what is the cause of the difference? So first, 2D X-ray photography cannot visualize the pitching corrosion. So this underestimates the steel weight loss when using X-ray photogram. Meanwhile, diameter of rebar not embedded in concrete estimated by X-ray is larger than that of embedded in concrete. So this overestimates the steel weight loss when using X-ray photogram. So we have to improve these problems. So now I could confirm that the applicability of X-ray photogram technique to the quantification of steel weight loss. So I applied this technique to the visualization of spatial distribution of rebars in RCB. So you can see this is a rebar, and this white part shows concrete. And this is a corrosion crack on the bottom surface of RCB. So as averaged, this is averaged steel weight loss. As the averaged steel weight loss increases, so you can see some localization of steel weight loss, and corrosion crack become wider, larger, like this. So I believe this visualization makes it possible to understand how non-uniform steel corrosion is generated. And this helps to improve the accuracy of estimation of corrosion distribution and the amount of rebar based on the crack width. So next, I present a hazard assessment associated with airborne chloride. So because the amount of airborne chloride attenuates with the distance from coastline, so the deterioration rate of breach depends on its location. So unlike the case associated with actions that are usually considered in structural design, such as seismic hazard assessment, there is a lack of research on environmental hazard assessment. So this is because the data on coastal airborne chloride is very limited. So anyway, we need to consider the differences in marine environment among breach locations. So these are typical and conventional equations used in the probabilistic seismic hazard assessment. So probabilistic density function of magnitude of earthquake and probabilistic density function of distance from seismic source and attenuation law are used in these equations. Attenuation rule means the relationship between seismic intensity and the distance from seismic source. This is an example of attenuation law. So peak ground acceleration adds seismic intensity attenuate with the distance from seismic source, like this. And this is an example of probabilistic seismic hazard curve in Japan. So you can see city A has higher seismic risk based on these hazard curve.